Hello. Hello. So you guys can hear me? Type in your chat box. Yes. Okay, good.
Yes.
Okay, thank you. How are you guys doing? So, well, from this lecture, this is week 11b. We are going to cover the very important part of our course. It's called digital controls. There are some unique concepts we are going to learn. And the importance is very clear that in a modern mechatronic system, almost all of them are mechatronic, okay? Mechatronic. So let's start, okay? Again, I'm recording this lecture, and today we don't have a quiz, and we're going to have quiz from next week, okay? So you're going to see that the reference textbook is, give me a second. Screen, this pen. So why my stuff is not working? That's strange. Okay, it's okay. So what is digital control? And what are the tools for the analysis and the design? And remember, we learned something called MAD, modeling, analysis, design. So we are going to talk about modeling today. So what are the practical issues in real world? Okay. So here's an outline of this module. We are going to spend 2 weeks on this topic. So first of all, let's recall what is a feedback control and the difference equation and solutions. Remember that we learned differential equation. So here we are talking about difference equation. And we learned S transform, the Laplace transform. Now we're going to learn Z transform. And the impulse transfer function, okay, and convolution in discrete time. And the sampling theorem, sampling, the consequences of sampling. We need to learn that. Then we need to understand what's the relationship between S and Z. So the zeros pose, and what is the zeros order holder, and discrete equivalence method about design. So why we need to do control? Do you guys can answer this type of question like you are in the barbecue party and explain to your neighbors, oh, what is feedback control? Okay. Feedback control is you change the system behavior such that the system will behave as you wish, okay? And the essence of the feedback control is to overcome what they call uncertainties, okay? Okay. So what are the tools? Laplace transform, and now Z transform. And frequency domain method like body plots. We didn't cover root locus, okay? For software tools, you are going to use MATLAB Simulink, okay? MATLAB Simulink. And this is widely used in industry as well, not only in academia, okay? The objectives in control answers the question about what do you want to achieve. So I want to achieve stability, zero tracking error, real steady state error. If I have disturbance, I can reject them. And I have a faster response, and I have little overshoot. All these are what we wanted, okay? What we wanted. How to achieve that? So MAD, okay? Start with a model. What do you know? Okay. And decide what do you want, the specification. Then what do you need to do? The structure. What is the structure of your controller? Or you have a PID, PI, or lead-lag. Then how to decide those controller parameters. Then you verify whether those specifications here already achieved. Then you should use simulation. So after everything is done, then we call this is the final implementation of control systems in the real systems. So that's the implementation part. So let's take a look. Traditional feedback loop, you have planned to be controlled, output is measured, and get feedback in here, you have set point, then you have a controller, okay? So this is the part you can include your smart ideas to put in a control such that the output respond to the set point nicely. What do we mean nicely? Nicely means, go back. Stable, zero tracking error, disturbance rejection, fast transient, okay, as fast as possible, and with little overshoot. But remember, I want to tell you that everything here, what we want, they are actually sometimes conflicting to each other. So therefore, control sometimes is also called an art of compromise or trade-off. Okay. All right. So then you know that computer is everywhere and the digital control is almost everywhere. Therefore, when you do a control, you have two important blocks. One is this blue block called ADC. One is this block called DAC. You have a good guess of this. It's called analog digital converter and digital to analog converter. So ADC, DAC. So this is digital signal going through this one, and this one is analog signal. Same thing here. This is analog signal. Then these are digital signal. Okay, so I like this photo because I like this block diagram because we have a human here, and I told you multiple times. And today, driverless car, unmanned systems are so popular. But no matter how popular it is still a special case of our Mechatronics system, right? But for any unmanned systems, there is at least one man behind, okay? So you should not think about there's no human anywhere. That's no good. So you should have at least one human supervisor monitoring this computer control system. So don't forget human in automation, okay? So we should seek the harmony between human and automation system. So instead of excluding 100% the human factors. All right, so, but in a real system, we want to control, it is usually analog, okay? Usually analog. But there are some systems that are intrinsically digital or discrete time. We're going to see that later. So in this case, our controller here, we would like to say this is a continuous time closed loop system. What we need to do is to build this one as a digital control system. So inside here, everything inside the box is digital. Outside is analog. So you have analog in, sampled. This switch means a sampler. Sampled, okay, then get to digital. Set point is also analog signal and sampled, and come over here. This is a digital. Your controller is a digital filter, basically. So this U is a discrete point, okay? But to make it continuous, you need something called ZOH, We're going to mention this one in a later part of the class. So it's called a zeros order holder. Let me see if I can write. It's called a zeros order I don't know why today my pen is not working. It's very strange. Oh, okay, now it's working. It's a connection issue. Okay, so it's zeros order holder. Okay, holder. So that is something to turn. I'll show you this one here. So you have a control signal, control, all the discrete points, okay? Discrete points. So you need somebody to connect them. So that kind of thing is a zeros order holder, okay? To make it this U at least looks like continuous, just not discrete points, okay? So these are the questions we need to answer. How fast should we sample? We're going to talk about sampling theorems, okay? Sampling theorems. This is the very important part, okay? Very important part. So when we sample and we obtain a sequence of data points, how do we represent the relationship between I and O? So that is, we know that we have an input or the output in a continuous time domain. I know that I have G of S, okay? Transfer function, okay? But in discrete time, what we should do? Basically, we need to start over from beginning, starting with difference equation, okay? And introduce the Z transform, how to solve the difference equation. And introducing the impulse response function and talking about sample data block diagram. This part, system ID, we're not going to cover in this course for a long time because building a system is a separate course called system identification, okay? I do have a module developed, but as I told you earlier, this course, we need to cover so many other missing pieces. So this module, I can give you the slides if you are interested. However, we did learn how to build a system model based on the reaction curve. So you have a reaction curve based on that. So you can get first order plus delay model, okay? So KLT model. So then, so this is basically we are addressing about MAD. So finally, we have a design part, how we can put this controllers together, how to design them. So we have several systematic way to do the work, leveraging the continuous time domain design method. At that point, I'm going to talk a little bit more advanced topics, okay? In a later, maybe after another 2 weeks. So what is in this part? We are going to talk about digital equivalent of the continuous time version and what do we mean digital equivalent. Start with Z transform and talking about Z transform, relationship between S and Z and how to do analysis and design the Z domain, okay? In the end, what you should learn of this module, understanding the issue of sampling. So lots of implications, okay? You will be able to implement a continuous time design in digital form, how you do that. Understand the problems involved, properties of digital systems, design the digital domain directly. So all these are very important skills, okay? So let's go through a difference equation, and I think you may feel this is too simple, but be patient. This is a very important entry point. Okay, let's start with a room temperature control. Okay, so you have lecture hall or classroom like that. You want to design the temperature control systems. One, have a good performance. Basically, you need to have what do you want? You want the system is stable. You don't want your temperature going up and down like crazy. Okay, or hotter and hotter. Okay, you need accuracy. When I say 70 degrees Fahrenheit, they will give me a 70 degree Fahrenheit, the desired temperature. And transient response, you got to respond fast. And robust, okay, robust meaning the system parameter may change. Say, for example, in the room, you have, right now you have 7 people, but what if you have 70 people in the room? So because when you have more people in the room, the whole thermal system becomes different. The parameters change a lot. But you cannot say, oh, my controller will not work for 70 people, only for 7 people, you know. So that's kind of robustness to the system's parameter changes. Make sense? Okay. So transient response, and what usually when you say, oh, when I say, oh, this is too slow, I want this one faster. But usually this should be like, well, you have something faster, yes, good, but you are going to have something like this. So you have faster, but at the price of much bigger overshoot. This is overshoot, okay? So slow, your overshoot will be smaller. So there's a trade-off, as you can see here, right? And need to be robust. I explained to you the disturbance about how many people in the room. And depending on the weather of the day, it's a cold day or hot day. You cannot say a room temperature under good control in summer, bad control in winter. You don't want that. And also then tolerate some modeling errors. So you don't have a very precise 100% accurate model, okay? Model accuracy. So because of that, it's never possible probably to do 100% accurate model. So that's why we previously said 2 interesting things in the quiz. The first thing is called all models are wrong, and some of the useful. If you get this model, get your job done, that's okay. You don't really have to have 100% accurate model. The second thing we talk about modeling is all models are wrong and some of them are dangerous. So just imagine you do a spacecraft training simulator, you use a wrong model, then everybody's trying to do this, but actual when you get into the aircraft, it behaves different, and so that will be disaster, right? So by this one, I want to remind everybody that for modeling, the purpose of modeling, purposes of modeling have 3 purposes, remember? Oh, I have multiple times. The first one is for you to modeling, like remember weather forecast. So modeling for prediction. So to see what will happen next. Prediction. The second is for control, closed loop control for modeling, okay? The third one is for education and training, like the simulator, okay? So I'm not going to write down. So the robustness also is required if you have some small problem in the sensor, some malfunction, then the system will still work. At least it will not blow up or smoke or causing a fire. Okay, so those are robustness. Okay, robustness. So remember how robust you are. Remember that if you cut yourself in the finger, and at a few days, that cut will heal, and you become as before, right? So therefore, you are robust to the cut. Okay. So here's the model. So basically, from the heat point of view, theta is the room temperature. That is the one we want to control. And but the real heat coming is room temperature minus theta A. Theta A stands for what? A stands for this A, ambient. Okay, ambient temperature. So then K times this one is the heat coming in. Okay, and this is the heat removed. Okay, so the difference is the temperature change. This is the temperature change. So it's C is some sort of a capacitor constant. Okay, it's like capacitor constant. Okay, here is related to the heat. So if we do Laplace transform of this one, and we know this side is so remember when you have a d dt, what you should be careful. So it's a s theta s. Okay, and then you have c times this one. But have you learned that we need to minus something called theta 0 minus, right? So this is the constant. So you also need a c in here. So with that, if the initial state is not considered, the theta 0 minus is not considered. So we just leave it there. So then we are going to have Cs theta s. Then here Q is like input. Q is like input, the heat coming in, minus the difference between this one times K. So using theta as output, Q as input, this is the disturbance, okay, disturbance. So with that, you can see there is a first order system in here. So what is the type of the system? It's a type 0 system because there's a s to the power 0 here, right? Remember, we ignored the initial conditions here. When theta is 0 minus, we don't consider, sorry, yeah, we don't, this is small theta, okay. The theta 0 minus is 0. 0 initial condition. Let me see what I have. WeChat chat box in here. Go to the previous slide. You can, this slide. Luis, why not you just ask? Open your mic, you can ask. It's okay, you can stop me. Can you hear me? Okay, maybe. Let's move on. So now we are trying to do a proportional control. This is KP here. So remember what we have here. This is a KP here. It's a proportional control. The proportional control. Oh, remember, I have a theta 0 in here. Okay, wait a minute. The theta 0 here showed up. It should be 0 minus, okay. But it doesn't matter, we can just, this is just a constant, okay, constant. But I'll put a KP in here. So SP here stands for set point, okay, set point. Okay, so this is a feedback, okay, feedback. But feedback, you said, oh, how about the previously you put H of S in here? But for convenience, we just put the 1 in here. But in practice, this one can be a number, but that doesn't matter. We can just transform into this way. Okay. So we have a type 0 system. You can imagine I have a type 0 system. I have a KP control. So then what we can say about the ESS, it will not be 0, okay? It will not be 0. So we have learned this before, okay? So you can see here, this one is actually called ET in here. So this is the signal here, okay? So the gain is kappa. It's not KP, it's a kappa, okay? Kappa is my gain. Gain times E, okay? Times E. With this, we are going to see what's the closed loop system. So with the closed loop system is like this. So this is my capital Q, okay? Okay. Because this QT is a feedback control. I put it here, yeah. So that's original K. So I'm going to put this one actually here. This is my Q. Therefore, this Q becomes this. I have this term minus this term. Then I just arrange. It is d theta. This is a theta dot. What is the theta? You have theta here. You have theta here. So it's a. I know I move this side. So it's a K plus kappa theta. So this thing is just constant. Okay, it's constant. And we ambient the temperature. We can see this is a disturbance. Okay. So basically, I have differential equation in time, okay, and it's theta dot theta and a constant in here. So I'm curious about. So this is my differential equation. I want to study what is my steady state, SS. So when we see steady state, basically we're saying that the theta dot is 0. It's nothing is changing. So then we just cancel this term. What's left is to write theta is this one and this one, okay, this one. Remember, K is fixed, but kappa, this kappa can change. So this one you can change. It's your controller gain, okay? So obviously, theta is not the same as theta SP, the set point. So therefore, there's an offset. In other words, steady state arrow is not 0. Okay, it's not 0. So in this case, anything in the ambient temperature change will also change the steady state. So we don't have the robustness to disturbance at the steady state. However, if you make your feedback gain huge, this is very big, such that the capital K can be ignored, then this is going to be 1. And this is going, because this is so big, this is going to be 0. So this is like 1 times theta SP, almost 0 times theta A. So you have to use very high gain. But there's a danger when you do high gain. You are going to give a huge input to your actuator. You only have a finite control authority, so it's no good. So in this sense, you can see transient. You can have you can increase the kappa. You are going to faster response. Okay. So if this is great, why we simply use a very big kappa? So you probably already learned there is a consequence. Okay, consequence. Okay, if you have a very small change in theta is the sensor measure the temperature. So it's naturally you can have some epsilon t as a noise. And this noise will be all amplified huge, okay, amplified huge. So then your actuator in this case is our vent to produce the heat. HVAC may not be able to deliver this large changes in Q at all, okay? And you can cause the system becoming unstable, okay? If you have a little bit of delay in the plant, okay, end up with an unstable system. So large gain is not a good idea. It's not a good idea. So here they just show you that you have changes in delta theta. Then you have delta Q needed. So this is proportional to K kappa. This kappa, okay. Minus sign here. So this is the case, okay. This is the case. So high gain is not a good idea, okay. It's sometimes it's not feasible, not possible. Okay, although, so we have to change the idea about whether the control structure. So there are many possibilities to do this on KP. P controller is only one. You can use a PI, you can use a PID, and you can use a lead lag controller like S+1, S+A, S+B. Okay, this type of controller. Or many others. In general, you have a C, okay, CFS, okay, so in general form. So there are so many choices. That's why control people feel proud, because they can have their own pick of CFS to do the job, yet they have a better sense of robustness. So that's why the control people and always feel proud, you know, because there are infinite many choices there. Well, let's go back and talk about our plant system. So this is our classroom temperature control. So from here is the Q to theta, okay? Q to theta. So this is a control signal. This is a ZOH. So this is a sampling. So this TS is sampling period. So this is up and it's like on and off periodically. It's called a sampler, okay? With a sampling time, sampling period, TFS, okay? So everything inside this dashed line box is called a computer here, okay? Computer. So this is a digital version of the system, okay? But what if we only can do something at the sampling instance? In between the sampling, I cannot do anything. Just put your hands off, okay? So the controller will also has the information at the sampling instance. So then input to the system is also only updated at the sampling instance. So we all live on this discrete dots, okay? Nothing will happen in between. We don't do anything in between the samplings. You cannot, because you are living in a discrete world. But doing this way, what's the consequence? So let's take a look. So we're starting from here. This is our starting point from here. So we have a continuous time differential equation. And we have time, and currently you have theta t. Then next point is theta t plus ts, okay? We use this finite difference approach to approximate the ddt. We get this one. By doing that, just replace d theta, we have a c d theta dt, okay? And I'll copy this side, okay, this side. So what I'm going to have is theta t plus ts So it's the next point. Then this is the theta t, current point. This is qt, current point. This is also current point. Okay, so let me draw this one for you. So you have t and t plus ts. Okay, sometimes they use capital TS, sampling period. So by writing this one, you don't see any differential equation. So this is called difference equation. Difference, okay? Difference meaning I only have, so this is theta t is here, and theta t plus ts is here. So these 2 points, okay, how they are related, I write down in terms of this equation. So this equation, you don't see differentiation, but you see differences, okay? So this is called difference equation. So by writing in a closed loop setting, and we write the current t, we counting the points, okay, is k, okay? Of course, t plus ts is counted as k plus 1 point. So that's why we replaced t with k, because we live with digital dots. So I only count the k. So instead of doing t, I don't use t, I use k, number of points, okay, different points. So this is a k, this will be k plus 1, this is k minus 1, and so on, okay? So by doing this one, it's more clear. This is a difference equation. But if we write in the closed loop way, closed loop way means your Q, okay? Q is proportional to like kappa times you have a theta set point minus theta. Here, actually, I use K here. Okay. By insert this Q, K, you are going to have this one. Actually, this is here. QK is this one. Insert this one here. You end up with this term. You have kappa in here. So this one is moving to copy to here. So then I rearrange. I write theta k plus 1, theta k. Everything inside this side is just a constant, okay? Because usually the ambient is a constant. This is also a constant, okay? If I use a set point, okay? So we should not treat these two as, but of course, this could be, in general, you can say, oh, this is another UK. It's okay, you can do that, but let's don't do that. So you can see I have a discrete time in here and TS in here. So now we are going to ask a question, what's the steady state error? What's the steady state, meaning when we have a k plus 1 minus theta k, they do not change, okay? It's 0. That's a steady state. So in a steady state, basically you set this one is a theta k as well, okay? This is theta k. So if the system is stable, we can always write theta ss, so theta ss, steady state. So this will give you, in steady state, that means this will be the same. Put it in here, your steady state will write something like here, okay? But remember, only kappa can change. So if you could kappa very big, this is 0. This is very big is 1. So this looks familiar, right? So you still have steady state error. Yes. All right, so we got an experience about discretization actually. Here, this is equation. Here is called, we are trying to turn the continuous time t into a discrete points. So this process is called discretization. Discretization. So remember, discretization could be more than one method, okay? This is just the basic Euler formula type of rectangular formula, okay? So we actually are having something like this. So theta k plus 1, we have seen that this is theta k. There's a constant in here. Then let's assume this is a constant as u bar. This is a coefficient alpha. Then we simply write a difference equation. So this is the first order difference equation. First order. I told you that if you can do first order, you can do high order, right? In the high order case, you simply turn high order into a vector form of first order, okay? So that's why the first order is so important. And what is the solution here? We don't know. We don't know. We simply just try and error, saying that it's a constant A0, A1, and R to the power of K. So this is something like a exponential, or no, this is a kind of geometric theories. So if we put 0 in here, K is 0, then you have this one, okay? So let's see, this is a general form. To solve this one, then we check what is A0, A1. So it turns out that theta k plus 1 is according to the solution. We have this, okay? And the theta k plus 1 is actually u bar. Remember, previously we have theta k plus 1 minus alpha theta k is u bar, right? So this is the first order difference equation. So I remove this one, this side. So I have this one. So, but remember, the theta k can still be written as theta k is a0 plus a1 r to the power of k. So I just alpha a0 alpha a1. So if you keep writing, keep going down, you in the end you write a0 is this one, and a1 is theta 0 minus a0. Okay, but in the end you can write theta k only in terms of initial theta and the constant u here, and this is the alpha. Okay, this is the alpha. You may wonder how this is coming from. Okay, coming from. So I think this one will give you some ideas. Okay, so the total response depending on the alpha is like a time constant. But here we should understand 1 minus alpha to the power of k divided by 1 minus alpha should be like this, okay? Right. So this is the response to the constant input. So this is like integrator. But why this is so, let me remind you something you have learned a long time ago. Let me do this, okay? So I want you to see, we have a summation of 1 plus alpha squared plus alpha k plus 1 minus 1. So I want you to see that if I do alpha s will be alpha plus alpha squared plus alpha k minus 1 plus alpha k. Okay. Now, I use this guy minus this guy, or actually using this minus 1 minus 2, you get 1 minus alpha. S is, you cancel out everything here, so you have 1 minus alpha k. That's why S is 1 minus alpha k divided by 1 minus alpha. Well, this S, I said, is this one. Can you see it's exactly this one? Okay. So that is, you just keep iterate. So you keep iterate. So you can continue to write things like that, okay? So we know that in this case, if alpha is very small, it will converge very fast, okay? If you have a large proportion of gain, your alpha is small. So in this case, alpha is, I said, go back to 3 slides. So I said here, this is the alpha. This connects to the T, okay, in the T. So if my T is, if my T of S is so small, that is 0, okay, then alpha is 1. Alpha is 1 is not going to work, okay? It's not going to work. It's not going to converge to 0, okay? So this is still 1, so everything will be 0. But if TS is too big, it is too big. So if alpha greater than 1, then this one, alpha greater than 1, then alpha to the power of k will blow up to infinity, okay? As k goes to infinity. So here, to check whether the system is blowing up, basically we see if alpha is less than 1, okay? So yeah, alpha is 1. Then in the end, the theta is like integration of my k, my u bar, okay? It's like an integrator. If sampling time is too long, then if you make the alpha greater than 1, yeah, then the whole thing will diverge, blow up. I use the word blow up, okay? So this story tells us TS matters, okay? Matters. If you don't choose TS properly, you have consequences. But on the other hand, how to make the TS is too small? You said, oh, I use a smaller T of S. However, the dollar sign, the cost will go up to buy some hardware to do a much higher frequency sampling, okay? But that is a reasonable knowledge that you know that it's too fast than necessary is a waste of money. Make sense? So you should not too slow, not too fast, okay? So how do I know then? So then we need to learn some of mathematics, okay? Mathematics. So in this case, we're going to do working with difference equation, and we borrow the idea of Laplace transform. So we use Z transform, okay? And we don't do locus here, okay? We don't do that. So let's move on to the next stage, formally the study on solving difference equation of first order. So usually first order is a scalar. Then for high order, you can convert to the first order. Of vector form. Okay. Then we should learn the Z transform and understand the impulse response function. Okay, let's start from here. What's the difference between what we learned here and previously? Previously, we say, oh, this is a constant. What if this is not constant? It's also changing with K. Okay, so this is a general situation, right? So basically, you have you can draw this as this is a UK going through a system. You also get XK out. Okay, and governed by this difference. First of all, the difference equation. How so? Alpha is a constant. Okay, the constant. Alpha beta constant. Remember, in our case, it's exactly this form. So this is alpha, and this is like a U of K. So the set point is changing. But remember, I said usually set point is a constant. Like in your home, you have 70 Fahrenheit. It's set up and it's not changing over K. But in what cases we need a temperature set point? It is not 70, but it's a curve like that. So this is like T, like set as P, T, K, let's say K. Let's do K is okay. So that's this curve changing. So this is the beta, okay? But this is a bias as a constant, usually, okay? If it is not, we can lump everything into a UK, okay? It's fine. So I'm going to explain to you, this is important to think. In what cases that you need the set point will change over time, okay? Like this one. So I tell you something. It is called heat treatment. Imagine you have a material, you have heat treatment, you heat up, keep it, and cool down. Then the material will have a specified property. But if you treat the material heat treatment like this, then the property will be different. Make sense? So in many of the process controls like pharmaceutical, like petrochemical, those plants, usually they need the temperature set point to be changed. And this kind of way of changing is called recipe. Recipe. Think about your cooking. Your cooking also set point is a temperature. Your cooking is also it's complicated. I don't want to talk about it. So let's try to solve it, okay? Remember, we started with something like this. We started with x k plus 1 minus alpha xk is beta uk. But they didn't use bracket, they use a subscript. That doesn't matter, okay? That doesn't matter to me. Doesn't matter to me. So this is, say, the subscript to save the brackets, okay? So let's do enumerate, enumerating, okay? We're starting from 1 until to k, so just brute force right from beginning. U0, x0, you give x1, U1, x1, you give x2, you know, okay? So then you have a x1 again here, then you put this one in here, you write in terms of x0 and u0 and u1. And keep doing this, you end up with something like that. So you only have alpha to the power of k versus x0 left. But in the end, you have a complicated form like this. But this also with some interesting formula. Say, for example, remember, if my beta UK, that this here, if this is something called U bar constant, then this one will be alpha k minus 1 plus alpha k minus 2, da da da, plus alpha 1, okay? For alpha and plus 1, okay? Then times U bar. But if the UK is changing over time, this kind of connected like that. But remember, beta is just a constant. Okay? You can move the beta out, okay? So then basically I use the notation J is 0, so alpha 0 is 1. And so you have beta. So this is alpha zeros, okay? And then this is 0 is a k minus 1, is a k minus 1, okay? So that's good. So you simply write this format. I want to remind you one thing, that is J is from 0 to k minus 1. So total k term is, so this total k term is same as this k term, xk. Another thing you should notice that you should put this index and this index adding together. This index adding together will give you k minus 1. Okay, I hope you observe that. So this is a compact notation. By doing enumerating the difference equation, you get this one. So this is actually the foundation of our next digital convolution formula. So I want you to observe J plus k minus 1 minus J is k minus 1. Okay, it's k minus 1. And the k minus 1 0 to 0, then it's a k. Okay, so these are the connections. And then we enumerate this one. So this is one by observation. So I hope you observe these. Okay, so with that, let's assume that I have a second order. So you have k plus 1, k, and k minus 1, and uk again. So what you should do is have a vector. This is a vector, is a boldface. This is called boldface math symbol. So k, this should not be k, boldface. This should not, this is a typo. I don't like it. So this should be not, it's just the italic, like it's the same as this k, okay? So then we assume y plus k, yk is set up as a vector. Then we assume we can write this whole thing in this format, okay, this format. So of course, so if I write yk plus 2, yk plus 1. So because this is k plus 1, it's oh wait, no, this is a 1k plus 1, sorry, plus 1, this is k. So then you have a yk minus 1, okay. So yk plus 1 is alpha 1 yk, alpha 2 yk minus 1. And yk is yk, okay. So yk is, this 1 0 means yk is yk, okay. So it's, so basically you say that 1x is minus, this becomes positive alpha 1 yk, positive alpha 2 yk minus 1, plus beta uk. So this is beta uk is 0. So this first equation yk plus 1. And then you have alpha 1 x yk alpha 2 yk minus 1 plus beta. So this one is to this is first order difference equation. in vector form. So I hope you feel comfortable here. So then I guess this is my phi matrix, this is gamma matrix, okay? You compare to the scalar form of first order difference equation. And then you define your yk is 1, 0. So this is called output matrix H. With that, you can simply write, so that is a second order, okay, second order system. You can do a second order system with, you have different terms in here. Okay. So you can see what's the difference. You have a k minus 1 here, okay? Can you see? You only have a k in here, but what if k minus 1? So you can just introduce uk minus 1, okay? So then you can write down that form, okay? So solving this matrix difference equation, it's similar, okay? It's similar. Again, we do a enumerating process, okay? And they will give you the similar one. So you can see this is a k term, which is this, and j plus this one, the index is k minus 1. So, and then output y is written in h. So this is my h. This is the same. So it's same as a scalar form. So don't feel this is too hard. In MATLAB Simulink, this is just so easy. So right now we can do original difference equation, solve it in a recursive form, but it's still very involved, okay? Involved. We hope we can do something in a similar algebraic form. That is Z transform, okay? Z transform. And we hope we can use all the techniques we learned in the Laplace transform method, okay? So continuous time system, we didn't directly solve the differential equation. We actually turned into algebraic equation, okay? So then use the transfer function concept. So then the temperature control, like this is a continuous time system. So we use a transfer function like that. So this is Laplace transform domain, okay? So therefore, we are going to learn the definition of Z transform in parallel to Laplace transform. So we are going to, so please pay attention. So this is called, you are giving a sequence, okay? A discrete sequence of X signal. So we call this a signal, discrete sequence, discrete sequence. And we define the Z transformation of this sequence, discrete sequence, as X of Z by literally doing X is kz to the power of minus k, and from k infinity to infinity. So this is called original definition of Z transform. But based on the assumption that this is this limit exists, okay, exists, okay, but it may happen that this summation sequence does not exist in the transform. We don't call that, but it's usually have a convergence domain, okay, domain of convergence, or region of convergence, ROC, region of convergence, okay. So let's do an example here. So we have, so this is minus infinity, this is positive infinity, these are discrete points. So the X sequence is these dots when, so this is like a heavy side, okay? Heaviside function. So it's a unit step function, right? So, but now you don't have a line here. You don't have a line here anymore. You don't have the line here. You only have discrete points, okay? Discrete points defined such like this. So no matter what is your k greater than 0, it's always 1, 1, 1, 1, okay? But we add this thing together, so it's same thing as from 0. And remember, from if you have something like this, you are going to write what? Do you guys still remember I did something for you? It's let's say Sn is 1 plus alpha squared plus alpha n minus 1. So then I know that this is what? 1 minus alpha n, 1 minus alpha, right? So I derived this one for you just now, okay? I told you how to do that. Then this is same here. We just put this one as n. Then we limit this one, send n to infinity, right? Infinity. But here is like alpha is nothing. Like alpha is just like 1 over z, right? 1 over z. Okay, this is alpha, right? Alpha. Okay. Then actually this is another z. No, it should be 1 minus 1 over z n, and 1 minus 1 over z. Okay. But this one we assume that goes to 0. Okay. That means 1 over z is less than 1. Okay, less than 1. So this is wrong. It should be say 1 over z less than 1. Okay. So not z less, z greater than 1. Okay, z greater than 1. What's going on with my pen? So then what's left is actually 1 minus 0, 1 minus 1 over z. This is z of z minus 1. So, okay. All right. So we know that for discrete step signal, its z transformation is z over z minus 1. So in other words, we say the xk and z minus 1 is z transformation pair, okay? Z transformation pair. If I have decaying, a is less than 1, then this is decaying, okay? Decaying. If a greater than 1 is increasing. And again, we don't consider anything below negative, less than 0. So what we do is the original discrete sequence is zk, then we do xk times z, we become this one. So then end up with this one. So this is my alpha, okay? So I'm going to do 1 minus alpha n, 1 minus alpha, okay? And send n to infinity. Then this should be 0, but alpha must be less than 1. In other words, a divided by z less than 1. In other words, again, this is wrong, and z has to be greater than a. Okay, greater than a. So then, what's we have here is actually we have a 1 divided by 1 minus alpha is a divided by z. So this will give us z divided by z minus a. Okay. 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 So I hope, although this is fundamental, it looks simple, but we need to remember the original definition is this, some operation here. You need to know how to summarize this. That's it. So, well, we have another 4 minutes. We can continue this Z transformation part, but I would like to pause here to see whether you have any questions. Okay, let me see if you have any questions. You can. Okay, I see part of the capstone group 5. That's a private question. After this lecture is possible. Yes. Yes. Okay. And Ariana? Yes. Yes, I can. Yes. Oh, it's private. Sorry. I just noticed. Great. So, any other questions? I'm recording this lecture, so I only see how many students in here. I only see 27, including myself. I have 14 people not showing up. So that's probably everybody has a reason not to show up. But I'm record that. But the next lecture, don't miss. Although this looks simple, but going through is much more effective than you read the textbook, than you read the slides. Okay, those concepts are hard to establish by your own. So with that, I'm going to say goodbye to you. So I'm giving you 3 seconds. If you have questions, without questions, next, when I count to 3, I'm going to quit. Okay. So 1, 2, 3, goodbye, and talk to you next time.